So if I didn't tell you these were ionic compounds, how would you know?
You have to look.
You'd have to look and see if they're metal and non-metal. So I'm checking my first element. That's where the metal should be. This is in the middle. This is on the left. So those are both metals. Okay. So that means my rules are I'm naming cation and then anion. And then it means that if I have anything in there indicating numbers, it's going to be Roman numerals. What do Roman numerals tell us? Charge or number of atoms? Charge. Okay. All of the anions, we know the charge because either it's a polyatomic that we memorized or it's in a column that it's from there. Okay, so this one we're going to say is vanadium. And then what's the name of this anion? Sulfate. Now I'm going to leave some room here just in case I need a Roman numeral. All right, so sulfate I memorized has what charge? -2. -2. But it doesn't appear in the formula, and that's because it's all balanced out. We've canceled out the positives with the negatives. So what I need to do is figure out what's the charge on this vanadium that's going to make those sulfates cancel out. And the way I'm going to do that is I'm going to say I have 3 of these, the number on the outside of the parentheses. I have 3 of the whole thing. So 3 times -2 is -6. So that means all of my vanadiums together have to be +6. And since I have 2 of them, what's the charge of the vanadium? +3. Yay. Now, can I tell that just by finding vanadium on the periodic table? No. So I'm going to have to put the Roman numeral here. Okay. Now this one, rubidium, do I know the charge of this one? Yes, because this is in group 1. Okay, so this is going to be a +1. I don't need a Roman numeral for this one. And then phosphate, I was going to tell you, what is PO4? Anybody know?
It's phosphate.
It's phosphate, yeah. And I don't need to do anything about charges on this. Now, what is the charge of phosphate, just so we know for our quiz? It is -3. And we can tell that because this is a +1. There's 3 of them. So that would be -3. Okay. So Roman numerals with ionic compounds, which means there's going to be a metal present, unless it's ammonium, but I didn't put those in compounds on the quizzes. If I have covalent compounds, I indicate the numbers with prefixes. So prefixes for covalent, but no Roman numerals. Roman numerals for ionic, but no prefixes. Except if we have hydrates. So there's one bonus question with the hydrate, and that is the only time you have a mixture of the 2. Okay, so you will have the question where you would name the hydrate, and if you would name the first part just like you would do this. And then if there were 7 waters, if it was .7 H2O, you would call it rubidium phosphate heptahydrate. So the first part, you just follow the ionic rules, and then you only use a prefix for the hydrate part. Okay, now let's talk about percent composition. So most of the time when we're talking about the percent of something, whether it's a compound or a mixture, we're talking about the percent by mass. That's not true of gases. Gases we tend to do by volume rather than mass. But for right now, we're not dealing with gases. So we'll just deal with mass. We can determine from a chemical formula, any chemical formula, what percent of that formula is the mass of each element. And that's very different from the percent that is the element. So if we think about water, there are 2 waters for every 1 oxygen. So it's 67% hydrogen. But if I look at the mass, instead of 67%, it's only 11% hydrogen by mass. Okay, so it's much, much smaller if I do it by mass. And that happens when the masses of the elements are very different. All right, we know that a percent is a part divided by a whole times 100%. when we are looking at the percent composition, I'm going to say of a compound. We'll get to mixtures later. When I look at the percent composition of a compound, the whole thing is the compound. And if I'm doing it by mass, the whole mass is the molar weight. So the bottom number is the molar weight of the compound. And the top number is the molar weight of the element, okay? So we might do something like, if we were looking at carbon dioxide, and I'm gonna CO2, we would need to know the mass of the whole compound. We need to know the mass of each individual element. So carbon, where am I going to find it? Periodic table, 12.01. Oxygen, 16.00. Now, the periodic table you have may have more digits than that, but use at least 2 digits after the decimal. If you start chopping off digits and you're looking at something like magnesium that isn't 0.00 or 0.01, then your numbers get off. So use 2 decimal places. Okay. So sometimes people get confused about what to do about oxygen because they remember, oh, it's a diatomic element. But in this case, this isn't in elemental form. The oxygen is part of a different compound. So whenever oxygen is part of a different compound, consider it one atom at a time. The only time you consider it as the pair is when you're just dealing with oxygen that's in the air, kind of oxygen. Okay. So I'm going to add these up. I only have 1 carbon in the formula. I have 2 oxygens in the formula. So I am going to multiply by 2, not because oxygen as an element is diatomic, but because this number is 2. And when I add those up, I get 44.01. All right, so that's going to be my bottom number. And then my top number is going to be for each element. So if I want to know the percent carbon, I would have 12.01 divided by 44.01 times 100%. And I get something like 27.29%. All right, now I want to make sure you guys have time for your quiz. So some of these, I'm just going to go ahead and tell you this. But if you have your calculator, you should pull it out and see if you can get the same numbers. Because if you're not getting the same numbers, the time to figure that out is well before the test. So you can figure out what you're doing differently than I am, okay? All right, now, 2 ways I can find the percent for oxygen. The obvious way is to do it the same way I did for carbon, but I have to remember that I'm including all of that oxygen. This is carbon. And so I would have 32.00 over 44.01. And I can plug that in. But what I should get is everything else between this number and 100%, right? Because the percents are those 2 things. So I should get 72.79% oxygen. Okay, so that's one way I can ask the question. That's not a terribly useful thing to do in chemistry. Sometimes it happens. More likely, you would be going in the other direction. You have some compound, some unknown compound that you know what the percent composition is by mass, but you don't know what the formula is, and you're trying to figure that out. So, how do you get the empirical formula? Remember, that's the one that's the lowest ratio formula from the percent mass. Yes. 72.7 7107. Okay. So it didn't add up exact. Oh, actually it does, because I just did math wrong. 29 and 71. Yeah. This is what happens when I try to do math wrong. Okay. Sometimes it doesn't add up, and that has to do with where we rounded our state phase. So if it comes out to a total of 99.98 or 100.01, that's okay. If it's coming out to 97% or 105%, then we have problems. All right, empirical formula. This can give us the ratio of the elements, which is what the empirical formula is. It can't tell us the molecular formula. So if our compound happened to be C2O4 instead of CO2, I'd still have that same ratio of elements and we wouldn't be able to tell from the percent composition. Okay, so it's only going to give us empirical form. All right, so how are we going to do this? We want to get to moles of each compound, just like you did in lab, okay? And you were able to weigh things out in lab, but here we're not weighing anything out. We don't have any masses. So we're going to make a mass by assuming we have exactly 100 grams. And the reason we do that is because it makes getting to mass very easy. So if I had 27% of 100 grams, how many grams is that? 27, right? The percent just becomes the grams. So if you assume you have 100 grams, each of the percents turns into grams for that element. Then once you have the grams, you can get to moles, just like we've been doing with our mole train thing here. You find the moles from mass for each element. And we're going to look at an example where we use a chunk, a sulfate, instead of just having the element. So you can do it for the parts as well. But our first example will be for each element. And then divide those number of moles by the smallest number of moles. The reason we're doing this step is to find the ratio. We want to know how the moles of one element compares to the other. Okay, so that's why we do that division. We divide by the smallest one because if you divide by something bigger, then you're going to have a decimal, right? If you have a little number on top, big number on the bottom, it's always going to be less than 1. We don't want that. We want 1 or 2 or 3 or 4. So we're going to divide by the smallest number. And hopefully that turns out to nice numbers like 2s and 3s and 1s. But if it doesn't, then we can multiply by a convenient small whole number. So if you remember the other day, we had 0.667. And we know that that kind of looks like 2/3. So we said, okay, let's multiply by the bottom of that fraction, the 3 on the 2/3, and that gets us where we're going. Okay, so here's our example. A lot of minerals, we knew the minerals existed for thousands of years, didn't know what atoms were, so we just called it by mineral name. So corundum is a mineral that is an aluminum oxide. So it has 2 elements, aluminum and oxygen. And it is 52.95% aluminum by mass. And our task is to determine what is the empirical formula of this compound. So our first step is to assume 100 grams. And then we're going to change the percents into grams. So for aluminum, we're going to have 52.95 grams. What about for oxygen? They didn't tell us the percent.
47.05.
And what did you do to come up with that?
You subtract the 100 grams.
Right. So just like we said for this one over here, everything else up to 100% is the oxygen. So we're just going to subtract the 2. So you said 47.05?
Yes.
Grams of oxygen. Okay. So that's here. Now we need to find the moles from mass. So remember where we're going to goes on top. Moles goes on top. And where we're coming from, grams goes on the bottom. And it's a good idea to not just put the units, but also put what chemical it is, because we're going to be comparing different things. And if you don't have your labels as to whether it's aluminum or oxygen, you're going to get things mixed up. All right. So this is going to come from the periodic table. So I look up here and see that that is 26.98. And that is for every 1 mole. All right, so what am I going to do for oxygen? 16, right? So it's not The gaseous oxygen we're talking about, it's the oxygen in this solid mineral. So it's just the 16. A few of you have your calculators out. I will tell you the first number of the aluminum moles is 1. Somebody shout out the rest of it.
1.96.
Yep, that's what I get. Okay, my grams cancel and I'm left with moles. This is still moles of aluminum, so I'm going to keep that there. All right, for oxygen, it starts with a 2.
Well, yeah.
Okay, that's moles of oxygen. Now, does this look like nice numbers that we can just say, oh, we're there, we're done? Not quite. Okay, so we need to get a better ratio. And so what we're going to do is this part, divide by the moles of each element. Divide the moles of each element by the smaller. So I'm going to divide by aluminum. One 1.962 equals 1 aluminum. So for every 1 aluminum, there's 1 aluminum. That's not very interesting information. The more interesting one is this one. 1.962 here. When I plug that in, I get 1.499 moles of oxygen for every aluminum. So I got to remember that I'm not just finding oxygen, but the ratio of oxygen to aluminum. So is this close to a whole number here? 1.49, is that a nice whole number? No, that's nowhere near a whole number. So we can't just plug that into the empirical formula. We're going to have to multiply by another number. Yeah. Okay, so this is pretty close to 0.5. So 0.5 reminds me of what fraction? A half. The bottom number on a half is a 2. So I'm going to multiply both of these by 2. So I'm going to have Al2O3. Now, why did I get 3? If I multiply 1.499 times 2, I'm going to end up with 998. This is very close to 3, right? If I round this digit here, that's going to make the whole thing turn into a 3. Very, very close to it. That's why I can round that. Okay, that's doing elements. we are going to try a little bit more complex one. I'm not gonna pause for you guys to call stuff out just so that we have more time for the quiz. This compound is going to be chrome alum. So it's similar to the alum that we worked with on Wednesday. Yeah.
I'm sorry. Can you like say one more time how we got 3 oxygens and 2?
Okay, so what I did is I took these two numbers and I multiplied them by 2. So 1 aluminum times 2 gives me 2 aluminums. And 1.499 oxygen times 2 gives me 2.998. And that is so close to 3 that I'm calling it. Yeah.
Is there a reason why you're multiplying by 2 and not by another number?
Because this is very, very close to 0.5. And 0.5 is the fraction 1/2. So that tells me if I multiply by 2, I'm going to get to a whole number. So if I had 0.33333, I would multiply by 3 because that would get me to a whole. And I have a handout, but I don't have it with me. So I'll give this to you on Monday, but this lists the fractions and the numbers you multiply by. So I'll give that to you on Monday. Okay. Let's go back here. All right. So if you don't have a calculator, start looking on the periodic table, find the molar mass of these two elements. All right, what's the mass of potassium on the periodic table? 39.1. What's the mass of chromium? Almost 52 exactly. We're going to call it 52.0. We've only got 3 sig figs here. Sulfate, we have to add up. Since oxygen is 16, so 16 times 4 plus 32 is going to give us 96, but sulfur also has an 06 on it, so 96.06. Anybody remember water from lab? Not 33, it's 18. Does that sound right? 18.02. Yeah. So those are the molar weights here. All right. We are going to turn the percents into grams. So we're going to have 7.83 grams of potassium. And we're going to divide by its molar weight. 10.4 grams of chromium. Let's see, 38.46 grams of sulfate. And 43.3 grams of water. Let me go ahead and keep the formulas here. Okay. Good idea for you to plug these in, make sure you're consistently getting the right numbers. But again, I want to make sure we have time for the quiz. So I'm going to tell you, it just works out that these kind of look pretty. So this happens sometimes. That doesn't mean that our formula is going to have 2s and 4s. These aren't whole numbers. They're kind of pretty looking, but they're not whole numbers. So we're still going to have to do the other steps. But what we can tell is that we will have the same number of potassiums as we have chromiums, and we'll have twice as many sulfates as we have each of those. We can tell that from those formulas. The water is 2.40. So what do we do from here to figure out the formula? Divide by the smallest one. So we're going to divide everything by 0.2. And it's going to be 1, 1, 2, and 12. Okay, so our formula then would be potassium, we don't need to write the 1. Chromium, we don't need to write the 1. Sulfate. But I don't want to just stick a 2 here, because then it looks like 42, right? So since I have a polyatomic ion, I'm going to do that, okay? And then for the water, it gets a dot and then 12. Okay?
What are the dots?
Because this is the ionic compound, so everything in here is an ion. This is positive, this is positive, this is negative. But this is a whole molecule that's sitting in that spot, so we do it a little bit different. This is also that weird time, and the only question on there is a bonus question where you would mix these, that this would use the rules with Roman numerals, so we'll find out chromium is +3, so it would have a Roman numeral 3 in its name, but the hydrate uses a prefix. Otherwise, ionic compounds don't get prefixes at all, but since this is a covalent compound, with water's covalent, we would put a prefix with that. Marcus, you had a question? No, just stretching? Okay. All right, so gotta put everything away but your periodic table. No polyatomic ion sheets out. If I take 2.4 and divide it by 0.2, the number's 12.
Oh.
So this came from dividing everything by the 0.2 was the smallest of those.
Why that line, that's very multi. Something in my head, that's 4.85. Okay.